Okay, there we go, streaming. Now, we should be sharing. Can you all see the website? Yep. Okay, cool. So I spent Friday and yesterday recording some new videos. They are designed to walk you through the process of being able to do your homework using the University of Iowa's virtual desktop. So I have two handouts. If you feel like you're able to figure it out on your own without the video, that's fine. But we have sort of the initial step of just getting connected. So if you're brand new to the university and you haven't learned all of these various procedures yet for connecting into university resources, that video will help you do that. And then I have 2 out of 3 videos ready for each of the programs, how to use SAS or STATA. You can pick which one you like, I don't care. Your advisor or people that you work with in your research for your program may have an opinion, so if you're not sure which one would be better for you, you can ask them, or you can ask me if you want my opinion based on what kinds of data sets you're likely to encounter. And the homework portal is also awake, and I posted a video for how to do that. So how many of you have successfully completed homework 0? Okay, looks like about half the folks. Did you have any problems doing so? No? What did you think? Think you like it? I've heard good things in that it's very gratifying to see the numbers turn green. It's like that instant win, right? There's so many things that we do in higher education where you just have to decide that it's good enough, but you don't know that it's like perfect, right? Perfect is the enemy of good. But this is one instance in which, no, you will have the right answer and it will be green and it will be finite and done. And that is a beautiful, beautiful feeling. Question from the audience: will the homework be for the next weeks be available in advance? Yes. So homework 1 is going to cover lecture 1 and the files from example 1. It will be at a minimum 1 full week after we finish talking about that before the homework would be due. I plan to get it up actually hopefully by the end of this week so that you can start working on pieces of it. You don't have to go through and do all of it at once. So my internet connection is unstable, it says. Tell you what, let me kill my virtual background because that may help free up some bandwidth. So sorry, I have to leave the beach, come back to my basement. Okay. So if you haven't had a chance to do homework 0, please take care of that by next week. I think the official due date on it is, yeah, the 7th, next Monday. The idea is that I want to give you practice using the system, make sure that each of you is able to access the system, and give you 3 points extra credit to start your semester off on the right foot. So that's the plan. So any questions about logistics, homework, videos, accessing the systems, and so forth? Okay. Please don't put off getting started on learning how to use the virtual desktop. Please don't do that to yourselves. I have had to troubleshoot, I think, at least every single person so far for something in the history of doing this because there's just enough permutations of operating systems and software and ways of connecting that it can be tricky. So please, if you haven't done so already, plan to do that. I think I have posted the videos next week and the week following. So that way, by the time homework 1 is due, which is not until week 5, you've had a chance to go through and iron out any difficulties in that. So, all right. Anything else before we jump back into content stuff? No? All right. Then tell me what you remember from last time. You can stare at the speech instead while we talk about that. I will take words, gestures, letters, phrases. What do you think? There's a prompt. What have we been talking about so far?
Well, I learned about some of the different abbreviations that are used. So PROC and FREAK. Is that how it's said?
That's how
PROC,
I'd say it.
and then FREQ. So for procedures and frequency, which seems
Yep.
pretty important to know how to start doing some of the coding.
Yes, that's SAS lingo. PROC stands for procedure, and I do say freak. So yeah, it's spelled differently than usual, but that works for me. Yeah, so frequencies. PROC freak, as an example, is how we get descriptive information for categorical variables. We've got some other folks chiming in. Very good. Histograms. Histograms are pictures, right? So there's two main types. You can have a histogram where each possible value of your variable is shown on the x-axis. That's typically used if you have a categorical variable or a small number of possible values for a quantitative variable. If you have a large number of possible values, it can be more helpful to bin them together, so to sort of chunk them, so to speak. And that is done using PROC Univariate, has a histogram option in SAS, or just the command histogram in STATA. Yes, indeed. Working with data sets and variables, yes, you'll get lots of practice with that. How to create tables and histograms in SAS and Stata. Yes, these are all useful skills. Run equals please, correct. Yes, there is no analog in Stata. Stata lets you be rude to it, but SAS insists that you say please. So every command in SAS is going to end with a run and a semicolon. For those of you who are familiar with SPSS syntax, the analog is the word execute. So if you've seen that before, run and execute do the same thing. There is no analog to that in Stata. Univariate, yes, so univariate means one variable, bivariate means two variables. Bivariate is a word that's typically used in the context of association. So that's the next lecture and example set is looking at how to measure associations between two different variables. Multivariate is 3 plus, correct. We don't, for whatever reason, we don't say trivariate very often or quadvariate. Is that even a word? Quintvariate? I don't, yeah, it's not a thing. Just like you can say that you have a number to the first power and then you square it and you cube it, like you don't fourth it, right? Like there's not a word for that, to my knowledge, unless any of you know of a to the fourth power quad it, then quint it. Nah, not a thing. So yeah, the numbers run out of patterns real quick. Don't use Excel, correct? You can use Excel to enter data, but don't use Excel to do analyses or data calculations. So for instance, if you need summaries across rows or summaries across columns, letting the computer do it within a statistical package is going to be a lot less error prone than you writing out formulas and dragging and dropping and copying. So yes. In previous semesters, folks had admitted they did all of their first homework via Excel to put off learning SAS and Stata, so it took them like 5 times as long as it needed to. I'm going to change homework 1 this year so that that doesn't happen. So yeah, we're not going to need Excel for anything. Um, Never treat categorical variables as text. Yes, so in storing data, try to use numbers because numbers are unambiguous. Even if you have a variable that is categorical, meaning that it's not really numbers, it's labels, using numbers to stand in for the labels will make it easier to enter information. You can always attach value labels, which is a system of labels that correspond to the numbers. You can tell the program that 1 stands for this, 2 stands for that, and it can show those labels on your results. That way you don't have to remember what 1 stands for and 2 stands for. But entering it starting with numbers is going to save you some trouble. Good. Lots of things. All right. Anything else that you remember? Okay. Then let us dive back in here. We had some pictures. So talking about summarizing categorical variables, we did that. Just knowing the frequency of the number of people that's in each category and being able to convert that to a percentage is sufficient to be able to describe a categorical variable univariately by itself. PROC freak is what the procedure is called in SAS to generate this information. In STATA, it's called tabulate. And I know that just staring at these sort of out of nowhere doesn't give you a sense of what it's going to look like when you're actually interacting with these programs. And that's why I recorded the videos. So what I did yesterday is actually walk you through what it looks like when you're inside these programs and you see these texts being written. There is a way to generate all of these written codes using drop-down menus, and it's fine to do it that way, but saving the results of what the drop-down menus generate, this is what syntax, is going to help you save steps in the future as well as create a reproducible set of analyses. That way you know exactly what you did, and you can write notes to yourself as to why. So we have proc freq, tabulate, on your homework, or note that the percentages need to be entered as proportions, so I corrected this typo. So if I have a percentage that's 45.59%, that needs to be entered as 0.4559 instead. Because when we start working with proportions and doing hypothesis tests involving them, they're always expressed as a proportion out of 1. So just to be internally consistent in how we're thinking about those numbers. Um, let's see, so more pictures for discrete data. That type of picture is not as helpful for quantitative data, and instead we want to do a histogram that lumps together values into convenient bins. You can choose how many and how wide they are to match the distribution of the variable. So in this example, for instance, this is SAS code right here. PROC univariate is a way to get a whole bunch of univariate information about a variable, as well as to generate pictures. So histogram is one of the options here. I'm telling it what the boundaries of the histogram are to be, 0 to 70, and then how many increments I need. And that generates a picture that looks like this. So this is from 2012 General Social Survey. This is a variable for personal income in thousands of dollars for that year. So most of the folks in the sample making under, say, $25,000 a year according to their self-report data. So in terms of being able to describe the information that's in a quantitative variable, it takes more than just a picture because eventually we're going to be generating models that try to recapture all of the information that's in a variable. So for quantitative variables, and just a reminder, what do I mean by that? What's a quantitative variable? I'm thinking of a three-word phrase. Continuous. Yes, that's a synonym for it. Leave missing data blank. Yes, that's another thing we talked about. Where does the 70 go in STATA? Question on this histogram. It doesn't. You tell it where to start and how wide the bins are, and then it decides where to stop. So it's just a difference between programs. But a quantitative variable, what is true about the numbers in a quantitative variable? Don't think too hard. We just talked about categorical variables where the numbers are labels, right? Like in this picture, let me go back. 1 stands for married, 2 stands for widowed, etc. Yes, three-word phrase. Thank you. Numbers are numbers. So a quantitative variable is what's known as interval measurement, where the numbers actually mean something. So quantitative variables may have boundaries, such as count variables that can't go below 0, rates or proportions that are bounded between 0 and 1, or they can be unbounded, but the numbers are numbers. So that's the main thing there. So in summarizing quantitative variables in which numbers are numbers, what do we need to know? 3 things. First off, central tendency. So 3 ways that people indicate central tendency of a quantitative variable: mean, median, and mode. So let me ask you a question and then I'll give you my favorite response from last year. I asked the class last spring, what's a mean? And my favorite response was from a student who said, the same thing it was in grade school? Correct. The mean hasn't changed. I did learn eventually that there is more than one kind of mean. So to be specific, I mean the arithmetic mean, But yes, you all know what a mean is, right? That's an easy one. So that's the average. Add up all the scores, divide by how many you added. Fine. Median. That is also a summary of central tendency, but it has a different definition. It's the middleist value, if you arranged all of the values in a row and picked the one that's exactly in the middle. Mode is most frequent. So all three of these things are ways to indicate sort of the middle central tendency of a variable. Sometimes they will agree, and sometimes they won't. Second, though, this is something that you may not have learned in grade school, and if you did, then I'm really impressed by your elementary school. Dispersion. How variable, how scattered, how dispersed are the scores? So, for instance, in the summertime, I temporarily have two children because my stepdaughter is here. So, if I told you that the mean age of the children in the house in the summertime was 9, that gives you a sense, okay, so she has some young-ish kids. But if I clarified that and said, well, actually, it's a mean of 9, but I have a 5-year-old and a 13-year-old, that's how I get my mean of 9. Now, that paints a different picture, right? Because if you think about what types of care and activities would be necessary for, say, an 8-year-old and a 10-year-old versus a 5-year-old and a 13-year-old, that's a different story. So just knowing the middle is an incomplete picture of most quantitative variables. We want to know sort of the spread around the middle. And there's two main ways that people do that in quantitative variables. One is standard deviation slash variance. Those go together in your head. And the other is interquartile range. So the standard deviation is the average distance from the mean of any given observation. That's in the scale of the original metric. Variance is the squared version of that. So you will see those two, one or the other, given to you, but they're on different scales. Standard deviation is in the raw units of the variable, and variance is the squared version. Interquartile range is the distance between the 25th percentile and the 75th percentile. That's something a little bit different, but it's the same idea. So for now, just think about the word dispersion and just think spread. Okay, that's what I want you to hang on to. Third is skewness, or you can think of this as asymmetry. To what extent is most of the data sort of piled on one side of the histogram versus the other? And that is going to color the decisions that you would make about what to do with that variable in an analysis. So note, I just fixed a typo a minute ago. This word right here should be analysis, not report. So it's something that we factor into what to do with respect to the decision making that would follow. So you all know what a mean is, right? That one you know? Well, welcome to notation that you may not have seen before to describe how it's computed. So remember when I said this is going to be language? This is a brand new language. This is your first crack at the brand new language. Notation. So to be very specific and unambiguous about how things are going to be calculated or estimated, we use a notational system that has usually letters, sometimes Greek letters, subscripts, and superscripts. So these have very specific meanings that you will get used to seeing. So y is a variable. We haven't distinguished yet kinds of variables of predictors versus outcomes, but basically if you're thinking about a variable that you're trying to summarize, we call that y. Okay, it could be any letter, but that's convention. This little subscript here, the I, the way that I'll say that is y sub I. That means it is a variable that each person has a potentially different value of, meaning it's not a constant, it's a variable. I stands for individual, so you can think of that as person. So y sub I is a variable, a column in your data set that has different values across people. N, in italics, big N, is the number of individuals in your sample. Y with a n subscript, or y sub n, refers to the last person in your sample. So we have y1, y2, y3, y4, dot, 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 all the way up to n. And so Uh, that is meant to abbreviate. As you can see down here, cheating ahead, the list of all possible people is abbreviated starting from 1, ending at n. And then last but not least, the mean. We use a notation system with a bar across the top. I call that y bar. This is the sample's mean. Note that it does not have a subscript because you're describing now the sample as a whole, as one unit, and so the sample has one mean. It's a constant. So the mean across the y sub I values is y bar. That's my sample's mean. Using that notational system to show how the mean is calculated, we have y bar is the sum across all the individual y's up to n divided by n. That summation process is abbreviated with the capital letter sigma. So the notation on the sigma, the bottom tells you where you start from, and the top tells you where you finish. So starting at I equals 1 and going all the way up to n, we want to sum all the individual y values. So this longer way of writing it, y sub 1 all the way to yn, can be abbreviated with this notation here, the summation, and then over n. So yeah, add them up, divide by the number of things you added, that's your mean. Okay, with me so far? That one's fairly straightforward. This is one of those things that you can do in Excel if you want to, although they don't have a mean function. You have to type average for reasons that I'm not privy to. Variance. So dispersion. This one, we're going to use the symbol s squared to indicate variance. Why? Because someone a long time ago decided on that, and that we're going to follow their lead. So variance starts with a summation, but it's a summation of a difference. So what we're going to do to describe variability, dispersion, and this is why I say when we review, I'll accept gestures, right? This is variance. Outness. It's each individual person's value on the variable, so y sub I, minus the sample's mean. So if you are someone who is higher than everybody else, your difference would be positive. If you're somebody who's lower than everyone else, your difference is negative. We don't want the positives and the negatives to cancel each other out, so we square them. So we take the difference of each person's value minus the mean, we square that thing, then we sum up those differences. Then we divide by the number of values that we summed minus 1. So this is the formula for variance. You can think of it as the number that describes how spread out all of the values are in a squared metric to prevent the positives and negatives from canceling. Because it's in that weird squared metric, though, it's hard to know what to do with a number like variance. It's like, okay, so my variance is 9. What do I do with that number? Well, it can be more intuitive to think about differences from the mean in the original metric of the variable. And so to do that, people typically take the square root of the variance, and that is the standard deviation, which is known as S. So if I have a variance of 9, the square root of that is 3. That's my standard deviation. So that tells me that any one person in a sample is going to be off from the mean by an average of 3. That's what it means. By the way, I need to take a quick poll. I have trained myself over time to say square root. How many of you think that sounds correct? Most people. Okay, how many of you grew up in the Midwest? See, those of us Midwesterners, you know that that's square root. Square root. That is how you say it. You go up on the roof, you drink root beer, you have a square root. That is how it is. And I've had enough people make this face at me like, ugh, that just sounds horrible, that I've trained myself to say square root. So I gotta take a vote. How many would prefer root? Looking for any yellow hands? Oh, just one. Root like butt. Nope. Yeah, root like boot. Yeah, it looks like square root. Is that the preferred pronunciation for this class? Okay. Yeah, well, those of you who voted, thank you for caring, but I will continue to say square root. Um, you know I'm tired if I switch, right? If I go back to my natural speaking patterns and root comes out, right? They call that code switching or something. This is a special language that we're speaking. So yeah, square root. I have to force myself. Yeah, thank you for not judging me. I don't feel bad, right? I didn't even know that that was a thing until someone pointed it out to me. There's other things that I've learned from interacting with other people that are Midwestern vernacular that I just accepted as like fact that they're not. So, for instance, if you go to the grocery store, remember when we used to be able to go shopping? Remember that? It feels like so long ago. But if you go to the grocery store and the cashier asks you if you would like a receptacle for your purchases, is that a sack or a bag? Okay, we have one vote for bag, bag, bag. Oh, the bags are leading so far. Sack is weird. See, so here's the distinction. It is a sack if it's temporary. Like you have a plastic sack. It is a bag if it's like a grocery bag that you bring to the store or your purse or a suitcase, like that's a bag. A sack is a bag that's throwaway. That's my definition. Yes, plastic sacks are meant to be recycled as holders for kitty litter or trash can bags or things like that, doggy bags, but they're sacks, they're not bags. So, yeah, it's a dialect. So if you're not from here and a cashier asks you if you'd like a sack, that they're referring to a temporary bag. So there's my education for the day. Midwestern roots. There's a brand called Sack. Okay, I'm gonna need to hear about this. There's a brand of bags called Sack. Okay, head blown. Yeah. Then there's also the difference between body parts. There's things on your body called sacks, and then there's things on your body called bags, and the bags are temporary, but the sacks are permanent in that context, which is just all kinds of messed up. Oh, yeah, soda versus pop, that's another one. That's a little more well known. Um, and there's also another version that's Coke. Even if you're talking about Pepsi, it's a Coke. That's in certain parts of the country as well. So, yeah, lots of differences in how we talk about regular things like square roots and square roots. But yeah, would you like a Coke? I'd like a Pepsi or Mountain Dew, but no. Anywho, yeah, I'm a Pepsi drinker in case you couldn't tell because there is no version of Mountain Dew that's acceptable to me in the Coke line or other ones. But so yes, Coke, pop, sack, bag, root, root. We got it. Anyway, back to statistics. We have the square root of variance is standard deviation. So it's just as important to find out how variable, how discrepant, how spread out the scores are from the mean than what the mean is itself. That's going to be just as important. You might be wondering why in calculating variance or its partner's standard deviation, the square root, we have this n minus 1 thing. The rationale for this is that we want to penalize the calculation for how many things we had to know in advance to be able to do it. So for instance, in this case, we can't compute what the variance is going to be until we know what the sample mean is. So we had to know the mean first, then we can get the variance. So we dock the sample size by 1 to reflect this idea that we had to know something ahead of time. Later on, that concept of how many things did we have to know in order to get this result is going to be called denominator degrees of freedom. So it's n when you're talking about the mean, n minus 1 when you're talking about the variance. If you had to know 2 things in advance, then it's going to be n minus 2, and so forth. So that's just a foreshadowing for those of you who've seen this stuff before. All right, so just visualizing what a variable would look like under different conditions of standard deviation. So I have a lot of pictures that I've made for this lecture to try and illustrate these concepts. In each of these cases, we have a mean of 100, but the picture on the left was generated using a standard deviation of 10. So the average case in this data set is off from the mean of 100 by 10. So that means the spread of the cases overall ranges from 70-ish to 130. Whereas on the picture on the right, the variance is 225, square root of that 15. And so the cases have a much broader range all the way down from 50 to 150. So you can think about the differences between these distributions sort of in two ways. Um, the way that I think about it is that in a given variable that has more variance, you are less certain what a good guess would be for any one person. Like if you think about the role of the mean, it's like if you know nothing else about a person and you have to guess what their variable is going to be, their score, the best guess you could make is the mean. Like that's the middleist value. Variance controls how wrong you're going to be about that. The more variance you have, the further off any one person is likely to be from that mean. So off by 15 on average, the standard deviation on the right, off by 10 on average, the standard deviation on the left. So how do we get this kind of information? Well, instead of PROC freq, which is for categorical variables in SAS, we want PROC means. There's more than one way to get descriptive information in every program. This is the one that gives you probably the most succinct version in SAS. So PROC means allows you to request different summary statistics for a given quantitative variable. So in light blue here, I've typed out the ones that I want for this example. N, what's N again? Vocabulary quiz. What's N?
The size of the sample.
Yay! Size of the sample. Capital N. Yes. Lowercase n is often used for subgroups in a sample. Like if I said I had 100 people and 50 of them were from group 1, it would be little n equals 50, but big N equals 100. Good. Mean, that's my arithmetic average. Statistical stands for standard deviation. Tricky. So here's your first instance of terrible human factors in these programs, right? Like the people that are the engineers and the computer scientists, maybe not the best guess for designing these systems. But var here is not the same as var over here. See the word var is twice in the same color blue? They do not mean the same thing. Var as an option within PROC mean stands for variance. Meaning, in addition to computing the standard deviation, I want you to give me the squared version. So down here in the results, under standard deviation, that value is 13. Its square is the 190. Min and max is just the minimum and maximum values. What data set the information is coming from is given on this data. And in SAS, data set names have two parts. Talk about this on the video. Work is where it is, what particular folder within SAS it's located, and example 1 is the name within that folder. Var in this context as its own sub-option stands for variable, meaning which variable column do you want information about within this work.example1 folder, within that data set, excuse me. So var here is asking which column. Var here is saying I'd like variance as an option of a piece of information for you to spit out for me. And run means please. So the variable that we're looking at here is income that we had a histogram for just a couple slides ago. On average, people make $17,300 a year in this sample, but any one person is expected to have an income that's off from that 17 average by 13. So if you go 13 in one direction, yay, that's $30,000. You go 13 in the other, okay, now that's 4,000. That's not so good. Now the fact that these numbers are creating an impossibility if you take it too far, right? So if you go 17 plus 13, within my ability to round in front of you and count, that's 30-ish, right? If I add another 13 to that, that's 43,000, right? I could keep talking about it this way. Well, what happens? Hang on, I'm a mirror. I have to remember that I'm mirroring you guys. You can keep going this way. This is positive. Well, what happens if I go the other way? I can go from 17 to 13. That gets me down to 4. What if I try to take another 13? Nah, you can't make negative income. I once heard a comedian do a funny bit about being overdrawn in their checking account, and he was saying, I don't have no money. Like I have to work myself up to having no money. And that may be possible at your bank, but it is not possible in this data set. So this is actually foreshadowing the idea that most of the cases are not in the middle. Most of the cases are on the low end. And so this descriptive in terms of the average distance may not be entirely useful for this variable for which you can't go too far on the low side. And indeed, the lowest you can have is someone who reported making $245 a year all the way up to $68,000 a year. For STATA folks, it's the word summarize. That's the STATA command that gives you this, and this is the information that pops out. One thing I didn't mention, this is just a housekeeping thing, NDES, that just asks for how many digits of precision after the decimal you want reported. It can keep your output from looking cluttered. STATA decides on its own how many digits to report. You can control that if you want to, but it's not strictly necessary. So, all right, how are we doing so far? So far, so good? Okay, so mean, the same thing that we had in grade school. Variance, probably something new. Did any of you remember learning about variance or standard deviation in grade school? No, I didn't either. Yes, one person. Okay. Excellent schooling. Congratulations. I did not have that experience. But extending from one sample back to the population here. So at the end of the day, it is rarely the objective to collect a sample of data just to talk about that one sample, right? We want to be able to draw some sort of conclusion about the people in the sample more generally. Well, that invokes a system of notation that then differentiates what a given value for a summary statistic would be in a sample versus what the analog of that would be in a population. So statistic is the word that gets used if you calculate a summary value within just the people that you have. So a mean is a statistic, a variance is a statistic. That becomes a parameter when you're talking about what it would truly be in the population. And so because of that difference, you will see differences in notation that go along with that as well. So adding on to our vocabulary lesson, if you want to talk about what you believe the population mean to be, that requires its own system of notation, and that's this U looking thing here. This is a Greek letter. It's not a U, it's a mu. That's what population means. So what we're saying is that mu for the population is being estimated by y bar for the sample. We have only the data that we have. We're making our best guess as to what the mean for the population would be. It's y bar. That's our best guess. We know that that's probably not right, but we hope that it's close. Same thing for variance. What variance is going to be in the population is another Greek letter. This little circle thing with the tail coming off of it, that's sigma. And it's sigma squared because variance is in a squared metric. Remember, variance is how far off each person is from the mean squared, summed across people and divided by sample size minus 1. And so our variance for the population, this sigma squared term, is being estimated by s squared from the sample. And if we unsquare it, we take the square root, then we end up with just sigma. That's standard deviation for the population is supposed to be approximated by s from the sample. So I think that's where s comes from. Standard deviation is abbreviated by s. There's a lot of things that start with s though, so that's maybe not the most unique choice. So when we talk about these things, and the rest of this lecture in particular, trying to hang on to the level of abstraction will be important because we have only one set of data. And even though we only have one set of data, we are nevertheless going to try to use it to extrapolate what the values in the population would be. And so critical to doing that is knowing sort of how far off we can expect to be from one sample to the next. That will help us to rein in our inferences to try and say, okay, it's a good estimate of the sample, I mean, it's a good estimate of the population, or maybe it's not so good. So we'll get there. One other thing you will sometimes find reported, coefficient of variation. I don't know what this means, to be honest. I don't find this thing useful, but it's something that someone may one day want you to compute. So I wanted you to know that it's just the standard deviation divided by the mean. So there we go. Okay. How are we doing so far? Are we still awake? Yes. Okay, black box people, are you stretching, manicures, doing dishes, folding laundry? Okay, yeah. This is my check to see if they're still there. Hello. You don't have to have your cameras on. I understand that kills a lot of bandwidth. I'm just trying to make sure that folks are with me. We here. Okay, excellent. If you do have questions, black box people, please feel free to use the chat window, and anyone can feel free to interrupt me at any time. All right. So more pictures. The third thing that you
I
might want
do
to
have a
know.
question.
Yes, where's that? Keep talking.
Sorry. It's Nikki.
Okay, there you are.
I'm trying to wrap my head around the coefficient of variation because, like you, I'm also trying to figure out what it's even supposed to be attempting to help you understand.
Honestly, I would have to ask Wikipedia. I don't see why it's a useful thing to know. So if anyone would like to do that and let us
I'm with you.
Okay. I've seen it reported. I'm sure that's something that you can ask the software to figure out for you. I just don't know what it tells you. Okay, yeah, I'll say more about that. Just
I could see almost like, yeah, I could see potential meaning like if you were dividing the mean by the standard deviation, but not the standard deviation by the mean. I don't know. Sorry,
yeah,
just you got me thinking now.
No, it's good to be thinking. It's so there's we're going to turn a page in just a second, which is why I'm trying to hesitate whether to bring this up now. But in describing how to characterize quantitative variables, we're going to end up using probability distributions, and they have different shapes to them. The one that we'll talk about in just a second is the normal distribution, which shows up everywhere. And it's the only one that I know of in which the mean and the variance are entirely separate parameters. Like they could each theoretically be anything. In all of the others that we tend to use in statistics, the mean and the variance are some yoked function of each other, where once you compute one, the other is sort of an extension of that. Uh-oh. I'm gone. I'm back.
Oh, hi. We thought we lost you.
I did. It disappeared. It said I was in the meeting, but then you all left. And now it just told me I'm the host again. So,
welcome.
Yeah, thank you. Let me figure out where I was here. Let me make sure that I'm still streaming. Okay, the stream is still going, so apparently the internet, it must have been a Zoom thing. I don't know. It could be that it's thunderstorming outside.
I just did the quick Wikipedia search, and it's basically representing the standard deviation as a percentage of the mean.
Okay. Well, you heard it here first. Coefficient of variation representing the standard deviation. What did you just say again? I've already lost it.
As basically a percentage of the mean.
Percentage of the mean. Okay. Someday, reviewer 2 may want that information from you, and so I want you to be able to give it to them and make them happy. We'll talk a lot about reviewer 2 in this class. Dealing with reviewer comments is a way of life. So yes, that's the coefficient of variation we were just learning about via the Google University. All right. So mean is middle. Variance and standard deviation is sort of how far out from middle the data tend to go. Are the data shoved to one side or the other is the third thing that you would want to consider in thinking about what to do with a quantitative variable, and that term is called skewness. Skewness is the amount of asymmetry of the data around the middle. And the formula for it looks like this. It is the difference between each individual value y sub I minus the sample's mean to the third power.
We can't
So,
see
oh,
your screen.
I have to reshare it, don't I? Thank you for speaking up.
Thank you.
Yeah, no, thank you. There we go. There, now can you see it? Excellent. Okay, yes, please let me know when I do silly things like that. But we have, this is slide 16 of lecture 1. Skewness is to the third power. So we had mean, which is unpowered, variance, which was something squared. This is to the third power. So you'll sometimes see these called moments of a distribution. That's just where the term comes from, is the squarest, or the exponent. I guess that's the word I want. But point being, skewness can be either positive or negative, and the wording that goes along with this is counterintuitive. The way that you label skewness is the direction in which the tail is headed. So on the left here, this is a variable that has a positive skew, meaning that like the part that's sort of the straggle is towards the positive side of the distribution. If there is no skewness, if this quantity that you can compute right here is 0 or close to it, it would look like this. And that's a symmetric distribution. I know the slide says symmetrical, but I just can't blame it's symmetric. That's another one we could take a vote on. I don't think we need the ul on that. But in this case, if the data have a symmetric distribution, there is no skewness, then the mean, median, and mode are going to be right on top of each other. So in that case, it doesn't really matter which one you think of as indexing your central tendency, because they're all going to tell you about the same thing. If you have negative skew, so everybody's piled on the right side, very few cases of a relatively low value, then it matters again. A lot of variables that you'll see that are quantitative that have some kind of natural boundary at 0 are going to have a positive skew, this one on the left. And so this is why when people report measures of central tendency for skewed variables, they tend to report medians, like median home price, for instance. Because what's the most inexpensive house that you can have, right? It's 0 at an absolute minimum, but what's the most expensive house you can have? As it can be anything. So median tends to be a more robust measure of central tendency in variables that are positively skewed. So in the example, for instance, here's my histogram of income. We had found out a few slides ago that the mean was 17.31, but the median is only 13.48. So the middleist value is actually lower. The mean, which would be about here, is being artificially inflated to some extent by all these rich people out here in the tail. So they're pulling the middle out. Oh, sorry, I got to do it your way. They're pulling the middle out. Mode is even further out in this case. And we have our variance, standard deviation, and this is where interquartile range also becomes a thing. Another way of thinking about the median is that it's the score at the 50th percentile. So if you want to think about extending that, the distance between the 25th percentile to the 75th is what's known as the interquartile range, and that can be useful to report in addition to standard deviation as a measure of dispersion. It's going to be less subject to being biased by these extreme cases out here. And regardless, you would want to always report the minimum and the maximum of any quantitative variable to give a sense of the overall range as well. To try and describe variables that have skewness and potentially extreme values, you may see a picture that looks like this. Have you seen a picture like this before? Anybody? Maybe? Yeah. So this is called a box plot. There are much fancier versions of this available nowadays. One is called a violin plot, I think, and there's some others that have they've taken this idea and run with it. So this is sort of an antiquated version, but it's still fairly standard to show. The box shows where the bulk of the data is. So we have the line across here is the median. This little dot in the middle here is the mean. And then we have the 25th and 75th percentiles completing the box. And then we have this thing up here, which is what's known as a fence. And that is denoting where the extreme values begin. And so I have asked it to show all of the extreme values. So there's a bunch of people who have a score that's the same here. That's why there's all these little dots going across. And then only 3 people at the very top. So rather than just talking about the middle and then maybe talking about standard deviation, if you really want to convey sort of the extent of a variable and pay attention to the fact that, just talking about the middle is going to be insufficient, a picture like this can be very helpful. All right, how did I get all of this information? PROC Univariate in SAS. So PROC means gives you basic stuff like mean, standard deviation, sample size. If you want the skewness and median, interquartile range, percentiles, all this other stuff, PROC Univariate will give that to you. So this is the same command that we had, let me see how many slides ago, it was a little ways. Let me back up. To make pictures with. Where was that? Here, slide 7, same command. It's still PROC Univariate. In this example, I ignored all of the output just to show you what the picture looked like under the histogram option. Now I'm focusing on the rest of the output that would be available to you under this procedure. So you can get a whole bunch of stuff out of this. So homework question. This is how you would be able to get things like median, right, which is the 50th percentile. Or if I asked you for skewness or kurtosis, it's another one we're going to talk about, is in here as well. And in STATA, the analog is still the same option summarized, but with a sub option for detail. So detail asks for more stuff, which is going to include most of what was on the previous page here, the median being the 50th percentile here. So you can get all of this stuff with a click of a button. All right, last one, you may hear this. I wanted to show it to you in case you've heard of it before, and after this you can ignore it. Kurtosis. It has to do with how flat or peaked the distribution is. In practice, it's going to be pretty hard to differentiate from variance. And question, is there info that STATA has, is there info that SAS has that STATA does or does not, or will all of the info be the same? For things like this, it will be exactly the same. If you get into advanced statistics that use iterative algorithms to solve for parameters, then in some cases the answers may differ a little bit, but at this level everything will be the same. It's just a question of finding which particular routine will give you the information that you seek. So if you just want to know the mean of a variable, there's like 16 different ways to do that in STATA. So what I'm showing you are sort of the most common routines. You may come across others that give you the same information. And if you find it, if you find the mean or the median a different way and it's the same one, then so be it. So, all right. So kurtosis is something that we don't tend to worry about in practice, but just so that you have it as part of your list here. Okay. So everything that we've been talking about today is with respect to quantitative variables where numbers are numbers, right? So what about categorical variables? Do we need to calculate things like variance or skewness for categorical variables? Here's what happens. So if you have a binary variable, meaning that there's only 2 choices, like pregnant or not, dead or alive, something like that, you can compute the mean, and that will be the proportion of cases that have a 1 value instead of a 0 value. The mean of a binary variable then is often called the proportion, and you will see the letter P used instead of y bar for the sample mean. So it's the same idea, though there's nothing different about it. For nominal variables, so do you remember what nominal means? That word? Unordered. So what's your favorite type of pet? What's your marital status? What academic program are you in? Things like that, where you might have 1 means this and 2 means this and 3 means this, but they're not numbers. If you have a variable like that, such as marital status here, you can ask the program to give you a mean, and it will be happy to do so. So I did that. The mean of marital status worked out to be 2.74. Who wants to tell me what that means? Yeah, exactly. The correct answer is no. Just no. These aren't numbers, right? These are arbitrary pairings of labels and numbers. But if I switched the order of these things, it would be equally valid to do because this is just a labeling system, but the mean would be completely different. So this is your first warning that the software programs will not stop you from doing stupid things. It is perfectly happy to do whatever you tell it to, whether that makes any sense or not. So for nominal variables, we don't need a mean. We don't need a variance. They're not numbers. That makes no kind of sense. All we need to know is the frequency of each category, and technically speaking, we only need all but one of the categories. So if I know that I have 734 people, and I know how many are in each of the 4 of the categories, I know what the 5th one must be. That's all we got to do for nominal variables. You may see means calculated for ordinal variables, but they should give you pause. You will see this a lot, but just keep in the back of your head that ordinal variables mean that the numbers aren't numbers. So if you have an item, for instance, and it's measured strongly disagree, disagree, neutral, agree, strongly agree, you might see someone report that the mean response to that item is 2.5, meaning that people were somewhere between disagree and neutral. But those aren't really numbers. You could have a coding system where instead of 1, 2, 3, 4, 5, it's 1, 20, 300, 4,000, 50,000, and that's equally valid because they're just ordered categories. But the mean would be very different in that case. So just keep that in the back of your head that people pretend ordinal variables are numbers, but that feeling, it should make you a little squishy to do that. For binary variables, though, since we can have a mean of binary variables, what about variance? You can calculate a variance for a binary variable, but you don't need to. Once you know the mean, you know the variance. So the variance is a function of the mean. The way that it is written typically is they say P is the mean. That's the proportion of 1 values. 1 minus P, not the mean, which is the proportion of 0 values, is called Q. And variance is just P times Q. So here's a table down here that tells you for a given mean in the first row, what the variance of that variable has to be. So they're yoked together. So this has consequences in terms of modeling choices where you want to pick a different strategy for variables in which the mean and the variance could be different things versus binary variables where the variance is determined by the mean and it's also going to be different as a function of the mean. So just sort of put that in the back of your head that the strategies that we talk about for quantitative variables have to be adapted for binary variables because of this problem. Variance is determined by the mean in binary variables. Variance is not a thing for nominal variables. All we'd have to do is report the percent for each category. All right. So intermediate summary. Univariate statistics to describe a variable's distribution, sort of central tendency spread and asymmetry in a sample. What would you typically report in a results section? If the variable is symmetric-ish, you'd want to have the range, so the minimum and the maximum. People typically report the mean, and the standard deviation or the variance. You just have to make sure that you label clearly which it is. I think standard deviation is a more intuitive number because that's the average offness of any one case from the mean. So it's in the metric of the original data. Message that my stream was disconnected. Okay, I am still here? For real?
Yeah, we see you and hear you.
Excellent. Yes, I got very well acquainted last semester with finding out the hard way that I was frozen because I saw like 15 people at the same time do this. Like that simultaneous like disgust face. It's like, "Oh, I must be frozen." That's what that thing looks like, cuz the simultaneous disgust would not happen if it was just a normal, annoyance or frustration with the material. But we're back. All right, checking the stream. Okay, the stream is reconnected. We're good. Okay. So mean, standard deviation, minimum, maximum. For quantitative variables, that's sort of your bread and butter. If you're concerned about skewness or outliers, basically there being extreme values that pull the mean or the variance such that you want to try and report additional information, that's when you might throw in the median as well as an interquartile range. Those are the things that you would get from summarize in STATA with the detail option added, or PROC Univariate in SAS, which has all of the additional things besides just the mean. For categorical variables, though, it's just the proportion of each category. That's all you really need. The percentage out of 100 or proportion out of 1. And it's helpful to report all the categories, even though once you know most of them, the one that's left is just a function of the sample size that remains. In terms of visuals, it's not often the case that you would show pictures for every single variable. Occasionally, you may want to do that if you're trying to make a point about just how variable scores are or just how extreme values that you have recorded. But histograms would be my recommendation for doing that in quantitative variables or box plots or violin plots. Bar graphs where you have the proportion or the percentage of each possible value would be sufficient for categorical variables. So up to this point, we're just talking about describing one sample. And sometimes that's enough, right? If you were giving a test and you wanted to report back to your students how people tended to do on the test, right? You might give the test average, you might give the range, you might say, I had this many people in the 60s, 70s, 80s, 90s, something like that, right? But if you're trying to make a jump from the data that you have to the population that you hope to think about, we need to know some additional stuff. So it's election season. Regardless of your political leanings, you're probably listening with interest to results from various polls, right? This poll shows this group up by 10 percentage points. Well, does that mean that that person's going to win in the general election? We don't know, right? It's one poll. Even if we accept the sample for the poll as being representative, like they've actually got a good cross-section of the people who are going to vote in November, is 10 points enough? Right? What else do polls often report? Usually on the graphic where the talking head is talking about it, they may not say it aloud, but on the graphic, there's a term that they use. If someone has a 10-point lead in the latest poll, what else is often on the graphic? Margin of error, yes, that thing. That's supposed to give us some indication of if the poll was repeated, what's the wiggle in that 10-point advantage? Is it a 10-point advantage with a margin of error of 1 point, meaning it would be like 9 to 11, in which case we still have a clear winner? Or is it a 10-point advantage with a margin of error of 15, in which case we have no idea what to predict, right? Those are different things. So just knowing the middle, so to speak, doesn't give us all of the information to process how reliable that estimate of the middle is. We need the margin of error. So that's where we're headed next. So from descriptive statistics to inferential. Descriptive statistics is what it's called when we're simply talking about one sample and that's all we want to do, right? This poll shows this political party with a 10% lead at the end, or 10-point lead at the end, right? If we want to talk about whether that means this person is going to be elected, that's inferential. Like we're going from the one sample up to the broader population. In order to do that, we have to have some way of anticipating what the results would be if we did our sampling procedure over and over and over again. We have to be able to characterize what is the expected wiggle, technical term and gesture to go with it, the wiggle in the results that we would have. And to do that, we make use of distributions. So you will hear me say the word distribution a lot. That is a shorthand for a probability distribution function. It's a shape. And we rely on these to be able to characterize how likely a given outcome is if we know something about the process that generated it. So if I know the mean and the variance of a variable, and I know the distribution that variable came from, I can predict how likely any one value would be. The same is true at a higher level of abstraction. So what we're going to be talking about is the distribution across samples of summary information. And we're going to use probability distributions to do that. If you're talking about a distribution that's continuous, rather than thinking about the probability of any one score happening or any one sample's results, we use the term likelihood, but you can keep probability in your head for that. It's kind of the same idea. It's just that you can't have the probability of an exact number for a continuous distribution. So here's an example. This is our new friend, the normal distribution. Have you seen this before? The shape, this is pretty ubiquitous. It is often called a bell curve. And the person who, I want to say, invented it or popularized it, last name was Gauss. And so you may see this called the Gaussian distribution. So Gaussian is a fancy way of saying normal. But this shape is a distribution function. What controls this shape is this equation down here. Now remember my promise to you on the first day. Do I expect you to have this memorized? No. Do I have this memorized? No, I do not. I think my husband does because he actually programs this stuff. He writes algorithms that do things, and so he tends to pick that stuff up a little faster, but I don't even have this memorized. What I want you to recognize is that on the left-hand side is a number, right? If you put in, so here's some of our notation here. Y sub I, right? That's the outcome value for any one person. So like my score on this variable minus the mean for the population, that's our friend mu. And then this thing down here, that's sigma squared, that's variance. So if I know the mean and I know the variance and I know what my score is, on the left-hand side of this equals pops out a number. It's the height. So it's the y-axis here. So how likely is any one score going to be if we know the mean is this and the variance is this? So the blue line, for instance, this is the distribution of how likely the scores would be if we're coming from a normal distribution where the mean is 0 and the variance is 0.2. So how likely is it if I am part of this blue distribution, how likely is it that I get a score of, say, 0.5? Well, let's find 0.5 on the x-axis. It's right about here. Reasonably likely. Not as likely as a score of 0 because that's the middle, but still pretty likely. Now, if I get a score of 4, how likely is a score of 4 within this blue distribution? Really not likely, right? Very unexpected result. So the role of these distributions is to tell us how expected something is. If I have the red one, that still has a mean of 0 as well. The difference is in the variance. The variance is 5 times as big. It's a variance of 1. So in this case, more extreme scores, like heading out from 0.5 to 1 to 2, those are relatively more likely under the red distribution than the blue. Yellow still has a mean of 0, but it's even flatter. So now a score of 4 is actually, it's at least off the bottom here in terms of likelihood. So the role of these distributions is to tell us how likely something is. And we use this to not only describe individual variables, but also to describe the behavior of samples. So this is where the switch in inference can get tricky. What we're going to be talking about for the rest of this lecture is samples. And if I have a sample that gives me a 10-point lead of one political candidate, how likely am I to have found a sample with that characteristic if the true lead were 0? Like, how likely is that? And that's where the margin of error comes from. It helps you locate where you are sort of on each of these different functions. So this is the normal distribution. You will see this shape a lot. One characteristic of it is that it is perfectly symmetrical, so there's no skewness and no kurtosis, which means the middle, mean, and median and mode are the same thing. Okay, so we're going to use distributions like this in this class. Normal is going to be the most prominent. I'll show you a couple pictures of others that you may come across in trying to characterize variables of different shapes. So the good news is that the folks in statistics who invented these things, they came up with all different kinds. So no matter how funky your data look like, there's probably a distribution for it. There's all the different kinds. So even though normal is probably the most common and it's the most useful in characterizing differences between samples, within any one sample, there's all kinds of distributions that are available to characterize quantitative variables. So there's a lot of flexibility. All right. So we are heading out of time. Questions or comments before we adjourn for today? No. All right, then hopefully what we have done today is expand upon your grade school memory of describing variables that are quantitative. Middle, you need to know mean, median, mode, but you also need to know distance from the middle. Standard deviation is your new best friend. How far off on average any one person is from the mean. So basically, how reliable is the middle as a good guess for what anyone's score is? The greater the standard deviation squared is variance, the more likely it is that any one score is going to be off from that middle. There's your take home. All right, then it is 1:45. I shall see you guys hopefully in 2 days. Right? It's garbage day, which means do not say have a good weekend. That's how I keep it straight. It's garbage day is Tuesdays on my house. Stay safe, please. Stay in your houses. And if you have to go anywhere, please wear a mask and be careful. It's dangerous out there. So take care of yourselves. See you next time.